Okay, let's take a look at where we're at. We're going to start chapter 5 today. The syllabus here. Tomorrow, do you know what lab we're doing? The what? Actually, that. Let's see. It's week 5 now. So 1, 2, 3, 4. Week 4 we had the exam. Week 5. Actually, you don't need your goggles, so we're lucky. We won't need our goggles this week, but we'll need them next week. Definitely, we'll need goggles, and also proper footwear. You should. That is, no sandals or open-toe footwear. All right, we're supposed to be starting chapter 6. Chapter 6 is nomenclature. That should go pretty fast. And then chapter 7 we should be getting into. But I think what I'll do for today is we'll finish off chapter 5. And then chapter 6 I'll talk about tomorrow in conjunction with the nomenclature worksheet. And then probably chapter 7 on Thursday, or Wednesday, sorry, not Thursday. And so that's the plan for right now. So let's go to chapter 5 here, which deals with atomic theory. We're going to talk about atomic theory over multiple chapters. So this is just the start. So these are the learning objectives. I'm just going to go straight to section 5.1, which deals with Dalton's atomic theory. So these are the basic components of Dalton's atomic theory. This theory, this was proposed when really quite some time ago, 17th, 18th century, 19th century. Well, anyway, certain things have been modified. So let's take a look at his original atomic theory, and then we'll get modern atomic theory. The original atomic theory, each element is made up of individual particles called atoms. That's the same. You know, atoms are will reach a finite limit. Matter is not infinitely divisible. But I saw some recent press on aliens, and so this reminds me of Dalton, you know, because at the time, had anyone seen an atom? No. When Dalton proposed this, no one had seen an atom, and so how do you prove it? Have we seen atoms?
Yeah, because you said that we could technically see them using like X-rays.
Have we seen atoms? We have seen atoms. We have seen you can take images of atoms, you know, with X-rays or with scanning, tunneling microscopes. You can get images of individual atoms. You can manipulate those atoms. You can move them around and do different things with atoms. And you can try to break them up into smaller pieces. When you take an atom and put it in an atom smasher, you've heard of these atom smashers? These atom smashers, what they do is they accelerate atoms so fast and smash them into one another. And when you smash them together, they break apart. But what they break apart is not into a whole bunch of little atoms. You know what they break apart into? Well, they break apart into smaller particles, but those particles are not atoms. Those particles are what we call subatomic particles. And so they don't behave like atoms anymore. And so if you take an atom and try to smash it into smaller pieces, it doesn't work.
Does they come back together like ever? Does you say like neutrons?
Certain things can come back together. It depends on how badly you break them apart. Like some things can come back together and reform what they constitute. But yeah, nowadays people have seen atoms. So the way I liken it is, you know, has anybody seen an alien? Yeah, maybe, but you know, would you say a large consensus of people have seen an alien? No, large consensus of scientists have seen atoms. So, but this is harkens back to Dalton's time. In Dalton, nobody had seen an atom. Nowadays, it's irrefutable. Atoms exist, but I think once the majority of people have seen aliens, then I think it will be irrefutable that aliens exist, right? But for right now, what evidence is there in support of aliens, existing? And so there are multitudes of evidence for and against it. And I mentioned Avi Loeb, the Harvard guy. He has some good evidence. I mean, he doesn't outright state, they're green aliens that are producing this. He just says these are probably extraterrestrial in origin, and they're probably not synthesized using normal, ordinary processes found. They must have been synthesized like we synthesize things or make things. And so that's some evidence. And there's other evidence that might be refuted. For example, Bob Lazar or Robert Lazar, who says that the aliens, alien spacecrafts are being reverse engineered, and the propulsion system relies on element 115. Did I talk about that too? So you have different people hypothesizing aliens, and they aren't all the same. Like Ari Loeb, he's just looking at the composition of some of these things, and how could you get a composition of this sort of alloy in nature. Versus Bob Lazar, who says, Bob Lazar is, he says he was trained at MIT and Caltech, but MIT and Caltech have no record of Bob Lazar or Robert Lazar ever there. But maybe it's possible. And then he worked at Area 51 S1, which is like this place where they keep alien craft there, and they try to reverse engineer. And apparently, yeah. So he's been around, but some of the other claims, Area 51 is a real thing. Yeah, that could, what they should do is they just should show it. I mean, and then if the majority of people see it, and seeing it and touching it, or, if it's there, it exists, then that's pretty irrefutable. Somebody might hypothesize otherwise, like maybe it is artifact. And so there are all kinds of hypotheses, and what you do is you sort through the hypotheses, just like Dalton did, and then he comes up with evidence substantiating his hypothesis here. And so it's the same thing. You're trying to convince people who haven't seen atoms that atoms exist. You're trying to convince people who haven't seen aliens that aliens exist. And what do? You have to have evidence in support of it. And so I'm sure there are people in Dalton's times who thought that he was crazy, I guess. But it turned out he was proven correct. Anyway, going back to this, each element is made up of individual particles called atoms. That's fine. Atoms are indivisible. Yeah, when they tried to smash them in an atom smasher, it didn't work. All atoms of one element are identical in every respect. Well, this turned out to be incorrect. But, when something turns out to be incorrect, what wins, fact or theory? Facts win. So what had to happen was either the theory has to be abandoned or has to be modified. In this case, the theory wasn't abandoned because those are correct. What happened in this case was the theory was modified. It turns out all atoms of an element aren't identical. So if you look at hydrogen, the simplest element, not all hydrogens found in nature are exactly the same. There are some hydrogens that weigh more than others, and that was observed, but they all behave like hydrogen. So even though you have heavier hydrogen, it behaves like the lighter hydrogen does. And if you have heavier hydrogen, then we could have heavier water molecules. But the heavier water molecules behave like the lighter ones, except they're just heavier. Have you heard of heavy water? No? You might not have heard it, but you drank some heavy water today. You know, chances are that you had some heavy water. Could you tell that you had some heavy water? No. What makes heavy water heavier? Because it has heavier atoms. But there's still hydrogen, so it behaves like hydrogen. And so all atoms of one element are identical. This had to be modified. Atoms of one element are different from atoms of any other element. That's true. So hydrogen atoms are different than helium atoms. They have totally different properties. You don't have to memorize any of these. Atoms of one element combine with atoms of other elements to form compounds, chemical compounds. So we know that. So we can just look at this or try to visualize this pictorially here. This is Dalton's atomic theory. An element is made up of atoms. All atoms of a given element are identical. Up to a point, they're identical in terms of chemical properties, but some are heavier. And do you know what atoms are made up of? The composition of atoms? Everything's made up of the quarks, but when we think of atoms, if we break up atoms, they're made up of 3 subatomic particles. The 3 subatomic particles that atoms are made up of are protons, neutrons, and electrons. And so the difference in the 2 hydrogens is one hydrogen has no neutrons, the other hydrogen has a neutron. Now the neutrons don't impact the chemical property, but they will impact the weight. And so the proton with the extra neutron there is heavier. But chemically they're kind of similar, so when you had water, you couldn't really taste the difference. Okay, we go on here. Atoms cannot be created or destroyed, or atoms cannot be destroyed or created. We have to qualify this. This is in chemical processes or chemical reactions. When we have a chemical reaction, the atoms just get rearranged, but they're neither created nor destroyed. In nuclear processes, it's different. In nuclear processes, atoms could be destroyed, that is, they decompose. So for example, uranium is what we call radioactive. Uranium, the nucleus is too big, and we talk about the nucleus as part of the structure. I'll talk more about it, but the nucleus is where the protons and neutrons reside, and it turns out it's too big. It becomes unstable. And so what happens with something like uranium is it breaks apart into smaller pieces, and it turns out it breaks into smaller atoms. One of the atoms is like a helium atom, except it's missing its electrons, called an alpha particle. And so chunks of the atom break apart. When chunks of the atom break apart, it's no longer the same element. What defines the element is the number of protons. Now, protons and neutrons are made up of quarks, too. Those are, but we are not going to break it down that far. For chemists, we're just interested in protons, neutrons, and electrons that make up the atom. For nuclear physicists, they're interested in breaking apart the proton into quarks, or the neutron into quarks. So we're not going to go that far. All atoms of any given element have the same properties. So, for example, hydrogen, all atoms of hydrogen have the same number of protons, and that must lead to the same properties. The number of neutrons can vary without upsetting its properties. Helium has 2 protons, hydrogen has 1 proton. And therefore, atoms of helium are going to behave differently, since they have a different number of protons. So all atoms of any given element have the same properties, including mass. Well, no, not including mass. The mass is going to be different depending on which you're looking at. Now, when we say properties have the same properties, we're talking about chemical properties which are going to depend on the number of protons. But if we're talking about things like mass or density, then they're going to be different. So if a hydrogen is heavier, then its mass is heavier and its density will be heavier. And so I'll just say, have the same properties, chemical properties, but mass and density might differ. Atoms of different elements may combine in a ratio of small whole numbers to form compounds. Do you know what law that is? We have simple whole number ratios. So this would be a 1 to 2 ratio. This is a 1 to 1 ratio. But we don't see. Law of constant composition just means it's always the same ratio. But simple whole number ratios, that's a different law. That's the law of, if you can read my writing here, law of multiple proportions. And so I think this, I don't know what that's supposed to represent. The law of multiple proportions here is this. This is one of the pieces of evidence that refuted the infinitely divisible versus the finite limit for matter. And that is, carbon and oxygen can combine in a 1 to 1 ratio or a 1 to 2 ratio. But if matter were infinitely divisible, why can't we just add a little bit more oxygen? Because we can have any amount of oxygen. If you can have any amount of oxygen, can't we just add just a tiny bit more? And so rather than getting a 1 to 1 ratio, we might end up with a 1 to 1.01 ratio. Or 1.02 ratio, or 1.03. What's preventing that from just adding a little bit more oxygen or a little bit less oxygen? Maybe we get a carbon to oxygen 0.99 ratio. If matter were infinitely divisible, it should be easy to get any ratio you want, right? If somebody were to tell you that you can, what would you say? You can only have sugar, let's say this is my coffee, you can only have sugar in certain ratios. Like, for example, you could have 1 coffee to 1 sugar ratio or 1 coffee to 2 sugar ratio, but you can't have anything in between. Does that make sense to you? No, I could have any ratio of sugar I want because sugar should be infinitely divisible up until I get to the smallest piece of a sugar. You know what the smallest piece of a sugar? Sample is, and the smallest piece is a molecule. So yeah, I could put 1 molecule of sugar in my coffee or 2 molecules, but I can't put 1.5. But you know, that molecules are so small, it's pretty much a continuum. And so normally when I think of sugar, I think I can put any amount of sugar I want, right? Even if I go, let's say, like I think at McDonald's, they have you request how many sugar packs you want. Or do they do sugar cubes or sugar packs? I don't know. You have to put in the number. And so even if I say, okay, I want 2 sugar packs, do you have to put in all 2 sugar packs, or can you just put in whatever you want? You could put in whatever you want, right? Pretty much. That's because it's a continuum. But for this, we can't put any amount of oxygen. It's either 1, 2, maybe how many next? 3, maybe 3, maybe 4, etc. So this was good evidence in support of atoms. Because if you didn't have atoms, then we should be able to mix these in any ratio we want. There should be nothing limiting what ratio we get. So when we study atoms, what do we want to know? For example, carbon atoms are different than oxygen atoms. They have different properties, right? And so when we're studying properties, what do we want to be able to correlate that with? So why do carbon atoms have different properties than oxygen? Yeah, we want to know something about the structure of the atoms and the composition. So it must be the composition and structure are different. And so how are the composition and structure different between carbon atoms and oxygen atoms? And so that's what we're going to look at next. And so the first thing we're going to look at is the composition. What are atoms composed of? Atoms are composed of 3 particles. Now those 3 particles could be broken down further into smaller pieces, but for us we don't. We're not going to break them down further. They're composed of electrons. Electrons are a fundamental particle. These don't get broken down further. That's it. Protons and neutrons might get broken down further into smaller particles, and those smaller particles are called quarks. But we're just going to leave the protons and neutrons intact and not try to break them apart. So one thing that we know about electrons are these are extremely light and extremely small in size, dimension. As far as mass goes, these are about 2,000 times lighter than the proton and neutron. So proton and neutron are massive particles compared to electrons. How about in terms of size? In terms of size, do you know how big an electron is? How many nanometers, how many picometers, how many angstroms an electron is? The size of an electron? Atometer? That would be a pretty good, reasonable you know. But this is weird. You know how big an electron is? It's 0 atometers big, or 0 picometers, or 0 whatever unit you want. It has no size. Is that weird? How could it have no size? It does weigh something. So we know how many grams an electron weighs and how many kilograms. If you're in physics, you have to use the kilogram mass. It's like 9.3 times 10 to the minus 28 kilograms or something, or 10 to the minus 31 kilograms. I forgot the number. But the gram mass and the kilogram mass is easy to forget. And so what we use is we use a different type of weighing system. The size is weird. Electrons are weird in general. We'll talk more about the weird things, weird properties of electrons. But it's a subatomic particle carrying a unit negative charge. And the unit negative charge just means it's a -1 charge. That's the unit. And there's an actual charge to this. There are units for charge. Units being the dimension of the charge, and that would be coulombs. It's like -1.6 times 10 to the minus 18 or 19 coulombs, something like that. But we just call it -1. And it has a mass of about 2,000 times. I rounded that to 1 sig fig. It's actually 1,837. This is 4 sig figs. So it's 1,837 times lighter than the mass of the hydrogen nucleus. The hydrogen nucleus consists of a proton, so it's 1,837 times lighter than a proton. Its symbol, we call it E negative. So that's the symbol here. Its discovery is credited to J.J. Thomson. So there's some stuff I had written here. I'll just leave up here. Maybe I'll just talk about it here. Blue. We have something called the AMU. AMU. Or abbreviated just U. And what the AMU or U is it's the atomic mass unit. Atomic mass unit. And the reason we use atomic mass units is because the metric prefixes become inconvenient. You know, how many do you want to memorize out? So, for example, atto is 10 to the minus what? 10 to the minus 18? Yeah, that's correct. But where are we at if we're at 10 to the minus 31? Do you know the metric prefix for 10 to the minus 31? No. We're not even going to bother with that. In fact, we're going to use a different unit entirely. We're not going to use grams. We're going to use U. What's the relationship between grams and U? So if I look at grams, 1 gram is equal to 6.022 times 10 to the 23rd U. That's kind of an odd number, but we'll talk more about how it's defined later. But in other words, if you took 1 gram and divided it into 6.022 times 10 to the 23rd pieces, then each of those pieces would weigh 1 U. So the question comes up is, how is the A and U defined exactly? So if we think about the kilogram, gotta watch out here. Oops. Did I catch everybody on the roll? Everybody took the test, right? Oh, okay. Haven't?
Wait, sorry.
Okay. Yeah, it looks like everybody took the test. How is the kilogram defined?
Oh, I remember like the question about like some metal looked up in some glass. But that was true because it's in France.
Yeah, there's some chunk of metal that weighs exactly 1 kilogram that's locked away in some vault. It's sealed in multiple bell jars to protect it.
Just trying to steal it. He's trying to steal it.
So if you wanted to know, let's say you bought a kilogram's worth of gold. How do you know you got a kilogram's worth of gold? You'd have to trust them, right? But can you trust them? Did they give you the right amount of gold? Well, what you can do is you can compare it with the, you can go to France, you can compare it with a kilogram there. And if they match, that is they're the same mass, then you know you actually got a kilogram worth of gold. That's how you know. And so we use standard, or you use what we call a calibration standard. We'd make sure our balance is reading correctly. That's how we know. But is that very convenient? No, it's not very convenient. And so do you know that that question is not 100% accurate? Because in 2017, they changed the definition of a kilogram. Do you know what the new definition of a kilogram is? They defined it differently so that it takes advantage of like electromagnetic forces. And so they have, I forgot what it was called. Yeah, I should take a look again. The new definition relates the kilogram to the mass equivalent of the energy of a photon. A photon is like a piece of light at a specific frequency. The previous definition of the kilogram is the unit of mass. It is equal to the mass of an international prototype of the kilogram, which is the chunk of metal. So they're relating it to this. And they have a special instrument that they use to do this. Oops, something went wrong. So apparently you could build this apparatus. You don't have to fly to France anymore. I think they might actually have these. You could build this instrument, and anybody could build this instrument. Does anybody have access to this block of metal in France? No. And so, and apparently, this looks very expensive, but apparently the cost of building something like this is less than $20,000. So for less than $20,000, you can have the new one. And I guess the kilogram is slightly different because when they use the forces here, you know, the frequency of light, I'm not sure what they're doing to do it. I have to look at this a little bit more. But when they're using this, oh, it's a watt balance. Here it is. So the biggest change is to the kilogram, which was set by a 143-year-old platinum alloy cylinder dubbed Le Grand K, housed in the International Bureau of Weights and Measures in Paris. The kilogram is now defined in terms of the Planck constant, H. We'll talk about the Planck constant, but later, which has been measured with extraordinary precision in recent years. Its agreed value will be set as 6.62607015 times 10 minus 34 kilograms meters squared per second squared. So in this constant, there's kilograms. If we can calculate these out, then we can get the kilograms. And with researchers able to make precise mass measurements using equipment such as a kibble balance. This is the kibble balance here. But it turns out that two masses aren't exactly the same. The mass of the kilogram from the kibble balance and the mass of the kilogram from the prototype kilogram are slightly different. And so since the masses have changed, has everything else changed? So let's say you bought an ounce of gold before the change, and then you bought an ounce of gold after the change. Are they the same? Well, it depends on how the ounce was defined. You know how the pound was defined? There's 16 ounces exactly in a pound. Now, did the definition of the pound change? Well, how is 1 pound defined? What weighs exactly 1 pound? You know, is there a sister chunk of metal? This is the kilogram chunk of metal, and then there's next to it, there's the pound chunk of metal. And the pound chunk of metal weighs exactly 1 pound. Is that how a pound is defined? You know what I used to think? I used to think that in ancient times somebody grabbed a rock and called that, okay, this rock will be 1 pound exactly. I don't know who that person is or where that rock is now, but that's how I thought. But do you think that's true? Do you think that's accurate? No. Actually, I don't know how the pound is defined. You could define it using physics, like they did the kilogram here. You know, a pound of force. You know, we could define it using physics. But I don't really care. There are certain definitions I care. Like, for example, a dozen. You know, I don't know. I didn't know where a dozen came from. But somebody told me this morning where a dozen came from. Do you know where a dozen comes from? Because I thought, why? That's kind of weird because, you know, you only have 10 fingers. Unless Unless there was something with six, you know, 6 fingers on a hand. Was there something? Or baker's dozen?
No, there's a baker's dozen, but your baker's dozen isn't even 12, it's 13.
The baker's dozen's 13?
Baker's dozen's 13.
Yeah, and then somebody told me, well, maybe there were 13 loaves that they could fit in the oven, something like that, or 12 loaves they couldn't fit in the oven. But I don't know.
I know for a fact that baker's dozen isn't 12, it's 13, so if you go to a donut shop, they'll always, that's why they always give you an extra donut when you get a dozen.
Oh, really?
Because it's a baker's dozen.
Oh, wow. Next time I'll have to get that. Krispy Kreme gives us free sample donut, right? That must be it then. Otherwise somebody, they may have been sued, huh? Past. Well, somebody told me that for each cycle of the sun, there are 13 cycles, I'm not 13, 12 cycles of the moon. So that's where it came from. I don't know. But there are certain definitions you need to know. One is the kilogram. You know the old kilogram. So I figured that this is still valid. It's still valid if these two weigh the same. But do they? Well, maybe they're close enough. Maybe they're slightly different. We need to know that type of stuff. And we need to know the definition of the AMU. So the pound you don't need to know, but where did the AMU come from? And what weighs exactly 1 AMU? So do you think next to we don't have a gram, but we have a kilogram. That's fine. But what weighs exactly 1 U? We know that this is to 4 sig figs. We know that there's 6.022 times 10 to the 23rd AMU in a gram. That's not exact. That's approximate. And so what we need to know is, how is the AMU defined exactly? What weighs exactly 1 AMU? And that we'll save for later. For right now, we're going to use the AMU. The AMU is the most convenient unit because, you know, a proton to 2 sig figs weighs 1.0 AMU. And a neutron to 2 sig figs weighs 1.0. These aren't the same. One's slightly heavier than the other. We don't have to worry about it. To more sig figs, if I wanted 3 sig figs, then you'll see there's a difference. One's like 106, the other's like 108. But the electron's about 2,000 times lighter. And so to 1 sig fig, this is about 2,000 times lighter. And it's 0.005 U. So these masses are a lot easier to remember than the gram masses. If we're doing the gram masses, those are a lot harder to remember. But in terms of AMU, they're easier. So the proton doesn't weigh exactly 1 AMU. It would be convenient. Let's set the proton to weigh exactly 1 U, or maybe the neutron to weigh exactly 1 U, or even the electron. If we set the electron to weigh exactly 1 U, then these would be like 2,000 U. And so it depends on how it was defined, which is going to dictate what these numbers are. But if the proton doesn't weigh exactly 1 U and the neutron doesn't weigh, but they're both close, what does weigh exactly 1 U? Does somebody know the answer to that? What weighs exactly 1 U? And the answer is nothing. There's nothing that weighs exactly 1 U. And so what do we do in that case? Is it defined? Well, what we do is something similar to this. You know, locked in that vault is not a 1 gram. Locked in that vault is 1 kilogram. Do we need to make a separate chunk of metal for 1 gram? No, we don't, because 1 gram will be 1,000 times lighter than the 1 kilogram. So we could figure it out. Exactly 1,000 times lighter. So the same thing happens with the AMU, but it's a little bit more complicated. Nothing weighs exactly 1 AMU. But there is something that weighs exactly 12 AMU. Now, is that 12 AMU, is that from the dozen, or what is that from? It's not from the dozen. There's no connection there, but we'll talk about it later. All right, the discovery of the electron is credited to J.J. Thomson. What J.J. Thomson was studying was he was studying cathode ray tubes, or CRTs. CRTs used to be a lot more common. For example, the old television sets are all CRTs, cathode ray tube screens. And, you know, I've been watching some of those old videos on aliens, you know, and they're looking at the radar screen. The radar screen that's scanning the sky, those are typically, in the old ones, are CRT as well, cathode ray tubes. And so there are mysterious things called cathode rays. And J.J. Thomson was studying these, and it turned out that, you know what the cathode rays are? Cathode rays just turned out to be a beam of electrons. That's it. But they have a strange name, cathode ray. And the strange name comes from the design of the tube itself. There are two what we call electrodes in the cathode ray tube. One piece of metal is positively charged. The other piece is negatively charged. So if you go and look at a battery, one end of the battery, or one piece of metal of the battery, is positively charged. That's called the cathode. The other end of the battery is negatively charged. That's the anode. And so we see cathode and anode here. And so if you have a battery, the battery generates what? Electricity. And electricity is the flow of electrons, right? And so here we have the cathode. Over here, the negative terminal on a battery is called the anode. We know that positive ions are called cations and negative ions are called anions. And so there's that parallel nomenclature here. The positive terminal is called the cathode, the negative terminal is called the anode. And when we generate electricity, and I think it was Thomas Jefferson determined that electricity is just what? Made up of the flow of electrons. And so the electrons are going to flow from the anode to the cathode. These electrons are negatively charged, so the electrons flow in this direction. And so the electrons are being pulled towards the cathode. So we need a piece of wire to do this. Can the electrons flow through air? That is, if we don't attach the negative terminal, the anode, and the positive terminal, the cathode, with some kind of wire or something else, will the electrons flow? And the answer is no, the electrons don't flow through air. Unless what? We can get electrons to flow through air by doing what? By increasing the voltage. So what is the voltage on this? The typical voltage on this is like 1.5 volts. And then we could go to 9 volts, etc. And eventually when we get to about 2,000 volts, 5,000 volts, do you know what happens? We'll get a little lightning bolt. The lightning bolt is going to be a lightning bolt of electrons going from the anode to the cathode. And so that's what happens in the sky. When you see a lightning bolt, that's what we call a cathode ray. And that cathode ray coming down from the sky is just going to be a beam of electrons. And the beam of electrons is going to the cathode. Right? I don't know if the electrons are traveling up or the electrons are traveling down. I think they're traveling down. Okay. But that's it. Now, lightning bolt is quite jagged. And so what we see is it's jagged because there's a lot of air molecules, and due to those collisions, the path isn't straight. The path is going to be jagged. In a cathode ray tube, we suck out most of the air using a vacuum. And in a cathode ray, the lightning bolt is completely straight. It's not jagged. And that's because it's at low pressure. And so let's take a look at the cathode ray tube here. I guess I must have closed it.
Do your students like explosions, cute animals, and epic science experiments? Then they'll love GenerationGenius.com, a new website that makes school science topics fun to learn. Get all our videos and lessons at GenerationGenius.com.
Okay, this
We
is
used
a
to have
cathode
one
ray
of
tube.
these,
What
but
it essentially
unfortunately it got broken. Otherwise I'd show it to you. Maybe I'll take a look and see. So over here we have the positive piece of metal, that's the cathode. Over here we have the negative one. And then we have a power supply. The power supply you crank up to maybe about 2,000 volts. A couple of thousand volts is enough to set up a lightning bolt through here. Now the lightning bolt's going to be straight, and it's not going to be as violent, you know, as this, because it's a lot easier to set up a lightning bolt in a vacuum than it is at normal atmospheric pressure. And so we generate that. And since this isn't so violent, it doesn't emit as much light. In fact, you know, the beam of electrons is quite small. And it's invisible. So to make it visible, in this cathode ray tube, they put some fluorescent material. And so when the electron hits that fluorescent material, it starts to glow. So we'll see a glow coming off the background. It's from when the invisible electrons hit that. When we see a lightning bolt, normally we see a lot of light because things get excited to high energy in a normal lightning bolt. So see what's happening here.
it's a vacuum chamber. There are no a beam that causes that.
Okay, this is the
fluorescent
cathode
stream
ray
to
here.
glow. Looks like a nice
It's
straight
going
line.
fairly
doesn't
straight
it?
to the cathode.
We call
So
that
it's
a
originating
cathode
over
ray
the beam of
because it
electrons,
emanates or
like that.
begins at the cathode and shoots across over to the anode. J.J. Thompson was working with
Our cathode rays
We
been
really
cracked.
didn't
This is a piece of
understand what
glass.
they were.
It's glass
I mean, we have
tubing,
electricity going in
vacuum,
one
so
side
kind
and
of
coming out the
imploded.
other, but there's nothing inside to conduct it. It's a vacuum.
Now, the first thing is
So-
this. The cathode rays are originating from the anode. And so what they did here was they changed this anode here, it looks like aluminum. So if they change the metal to steel, iron, anything that conducts electricity, even graphite, they always got the same cathode ray. So it didn't matter what the anode was made out of. The result was the same cathode ray. And therefore they thought, well, whatever it is, it has to be a component of all matter. Even though they didn't test everything, because if they used diamond, it wouldn't work. If they used glass, it wouldn't work because those don't conduct electricity. They don't conduct electrons. And so, but all the other materials work, so they just inferred that all matter contains electrons. From that. And then the cathode rays, what else do we want to know? We want to know the charge, and we want to know the mass, and we want to know the size of the
He
electron.
decided to apply a magnetic field
And
to
so
this
here,
cathode ray.
it looks
And he
like
found
he's going to
something
take a
interesting.
magnet.
We apply
So if you
one
take a
pole of the
magnet
magnet
and
to this
bring it
beam, and we'll see
close
what it does, and then we'll flip it around
to
and
the
see what the other
cathode
pole
ray
does.
here, it's going to deflect it.
This
Do you
is
see
my
that?
favorite part. Can you
The
see what's
beam
happening
gets
to that
bent.
beam?
And if it's
Those- here's
negatively
those
charged, it gets bent this
happening to
way.
it.
If it's positively charged,
It's moving,
it gets
it's being
bent the opposite direction.
Repelled, isn't it?
And so
by the
based on
magnet.
which pole of the
We flip the
magnet,
magnet
north pole
around,
or
and
the
what do you
south
think's gonna
pole,
happen
it's
this
going to
time?
deflect it one way or the other.
Well, if it's being attracted
So
on
now
one pole,
they're deflecting it
see what's being
out around
attracted
that
there?
way.
Let me rotate it so
We
the
can
kids
just
on
play
this
with
side of the room can
magnets
see
to
it.
see.
See how it's being attracted there?
And so
And
that's
then
going
the
to
other pole, you
indicate
see how
the
it's being
charge.
pushed down? What does that tell me about that beam?
Not only that, you can put a target.
It has a what?
So if you put a target like a piece
It
of
has
metal
a charge.
in the beam,
Let me tell you about the
metal
poles of the
acquires
magnet.
negative
The one
charge.
that pushes it away
So
is the
that's
negative
further
pole.
evidence that
So what
these
does that tell you about
particles
the
are-
charge of those particles?
are negative.
Negatively
charged.
charged particles. And J.J. Thompson was
And
actually
so that's
able...
basically it for this. So based on this, J.J. Thomson was to state that electrons, cathode rays, are a fundamental part of all matter. We don't call them cathode rays, we just call them electrons in this case. And they're negatively charged, but did he weigh them? Is it possible to weigh an electron? No, it's very difficult, but there's some physics involved in here, and that is, it depends on how heavy the electrons are. If the electrons are very light, they're deflected at high angles. If they're heavy, then they aren't deflected as severely because of inertia. You know, the heavier ones are hard to turn, the light ones can turn rapidly. And so based on the angle of deflection, some physicists were able to calculate the charge to mass ratio. Once they figured out the charge to mass ratio, then there was another experiment that was pivotal, and that was called the Millikan oil drop experiment. The Millikan oil drop experiment is not discussed in our book, but Griffith Observatory has a Millikan oil drop apparatus. And what Millikan did was he got an aerosol of oil drops and then charged them with electrons. There's a way to shoot electrons like those using radiation. And based on how rapidly they fell in the presence of gravity and an electric field, you put a positive plate up here so the electrons could get attracted to the positive plate. Based on how they fell, he was able to determine the charge of an electron. Once he had the charge of an electron, then we had two unknowns, the charge and the mass. They were able to calculate the mass. So the mass was calculated based on the angle of deflection, which gave the charge to mass ratio, and then somebody figured out the charge, and then the mass was just calculated using dimensional analysis. And that's where we are for now. So, all you have to know is that J.J. Thomson discovered the electron here. What about the proton and the neutron? So I'm going to skip this slide for right now, and then we're going to come back to that slide. And so atoms are made up of electrons, protons, and neutrons. The proton was discovered by Rutherford. You don't have to know this, so we're not really going to talk about it, but he discovered it using cathode ray tube also. And it carries a positive charge. It's much heavier than the electron, and the symbol is just P+. The neutron also is much heavier, 2,000 times heavier than the electron. And the symbol for neutron is N0. For zero charge. These were discovered by James Chadwick, though. These two discoveries we aren't going to discuss. The only one we discussed is the electron. Okay. The mass of the neutron is approximately equal to a proton. Here we want to know the approximate masses. What are the approximate masses of the proton, neutron, and electron? The reason we want to know the approximate masses is because those aren't too difficult to remember. And so what were the masses there?
Mass or the charge?
The mass.
The charge is 1.0 U.
Yeah. Which one was 1.0 U?
The proton.
Proton. Proton and neutron were both about 1.0 U. Not exactly the same. And the electron was 0.005 U. Okay. All right, so the picture's not complete. You know, yes, there are experiments involved in the discovery of the proton and neutron, but you don't have to worry about them. Okay, the next thing we're looking at is, okay, the atom's comprised of protons, neutrons, and electrons. Now, how is it structured? Because we want to be able to correlate properties with composition and structure. And so the next thing we're going to look at is the structure of the atom. The structure of the atom, there are two hypotheses proposed. Let's say one was the plum pudding model. The plum pudding model is a case where we have the negatively charged electron particles are embedded within the positively charged spherical gel. So in the plum pudding model, the plum is the protons. The protons are spread out in this homogeneous gel, and it's spherical. That would be the atom. And the electrons are like the plums, and the plums are dropped or embedded in the pudding. Well, Rutherford did an experiment, this very famous experiment called the gold foil experiment. So Rutherford's gold foil experiment. It's a gold foil scattering experiment. And so what Rutherford did was he put some radioactive atoms in this. This is either lead. It's probably a lead container because radioactive atoms are unstable. And sometimes those unstable atoms can break up into smaller pieces. And one of the smaller pieces it can break up into are alpha particles. Alpha particles are chunks of atoms, and these chunks of atoms, bigger atoms, are themselves atoms, and they're atoms of helium. Mm-hmm.
So
What are alpha particles?
Yeah.
Let's say you have a big atom, and this big atom breaks up into smaller pieces. And one of the smaller pieces has 2 protons. If you have 2 protons, then that defines it as helium. And so what happens are 2 protons and 2 neutrons break off this bigger atom. So 2 protons and 2 neutrons break off. Those 2 protons and 2 neutrons are called alpha particles. And there are no electrons. Alpha particles have no electrons. And so what we say is an alpha particle is, later on we'll talk what the nucleus is, but we say it's the nucleus of the helium atom. But these are very reactive. And so this is part of particle radiation. So these alpha particles, these small chunks of atoms, break off and are shot out of, there's a hole in the source here, and they're shot out as a beam. And so this would be like cathode rays. Cathode rays are a beam of electrons. Alpha rays are a beam of alpha particles. And this beam of alpha particles hits the gold. Most of the alpha particles go right through the gold. And so the conclusion there is that the gold must consist mainly of empty space, because most of the alpha particles go right through and don't hit anything. And so the gold atoms must consist mostly of empty space. However, some of these are slightly deflected, and some are severely deflected. And so what the thinking here is the ones that are severely deflected must hit this concentrated region in the center. And the concentrated region in the center is called the nucleus. And the nucleus contains all the positive charge, that is all the protons, and all the neutrons here. Now, the reason the alpha particles bounce off is not because it's heavy. The reason the alpha particles bounce off is because the alpha particles are positively charged. And the nucleus is positively charged. And so if the alpha particle is positively charged and the nucleus is positively charged, then what we have is a repulsion or attraction. It's a repulsion. It's called a Coulombic repulsion or electrostatic repulsion. And so like charges repel. This is like trying to force 2 positive poles of a magnet together. They're going to repel each other. And so here, this is due to electrical repulsion here. Not because it's heavy. It is heavy because the protons weigh 1 U and neutrons weigh 1 U. And so basically, this experimental evidence here does not support the plum pudding model. If this was the plum pudding model were correct, then the positive charge would be spread out over the entire sphere, and so we'd have a plum of protons, and the electrons would be like little raisins or pudding, little raisins in the pudding. And so we expect small deflections, depending, but not large deflections like this. And so what that meant is that the experimental evidence did not support the plum pudding model.
Wait, so I'm confused. What is the plum pudding model?
Oh, what is the plum pudding model is what people are trying to figure out is the arrangement of the protons and neutrons.
So they thought that it was at the nucleus that the electrons were at the nucleus?
They thought, I'm sorry, can you repeat that?
So did they think that the electrons were at the nucleus?
No. Let's draw the plum pudding model. The plum pudding model is if you take an atom like this, where are the protons? First off, where are the protons? In the plum pudding model, the protons are spread out over the entire volume of the atom. So where are the protons? The protons are spread out. This would be like a gel, a spherical gel. And the spherical gel is all positively charged, like this. And so this is the protons. Now, where are the electrons? The electrons, let me go with a different color here, would be the plums. I call them the plums are kind of big, so I call these the raisins. I guess you could call them the plums. The electrons are just sprinkled in there. So it's kind of homogeneous. If you spread out the raisins, so it's uniform in there, but then it's also heterogeneous because the raisins are different than the the pudding. So this is the plums. And so this would be the plum pudding model here. Now the neutrons would also be spread out over this. So put in the neutrons here. Neutrons would be spread out like the protons. Now what we're doing is we're going to shoot alpha particles at this. So beam of alpha particles. The alpha particles, this is the symbol alpha, have a 2+ charge. So as the alpha particles, they're going to kind of be repelled by this, but they don't bounce off. You'd expect them to bounce off because this is positive, but this is also positive. And the reason they don't bounce off is because the positive charge has been spread out uniformly throughout the sphere. It isn't concentrated. So yes, there are repulsions, but these could kind of push through maybe. Maybe they'll be deflected. But we wouldn't expect large deflections like this. If you take all that positive charge and then concentrate it into a small volume right in the center of the atom, here. So now we take all this positive charge and concentrate it in a tiny volume here, then we could expect to see high angles of deflection. So now if the alpha particle were to come in and hit the nucleus, then it would bounce off. If the alpha particle comes in and gets close to the nucleus, then it will be deflected slightly. If the alpha particle is far from the nucleus, then it's just going to go straight through. So these are alpha particles here.
So is the concentration of the positive charge make it like I don't know, would be like, not attraction. What is that like?
The force, would be more significant. This is Coulomb's law. Is the force is proportional to what? The charge, the magnitude of charge on A, and the magnitude of charge on B divided by the distance squared. And this is going to be related to the charge density. So let's say you have a positive charge spread out over a large volume versus a positive charge spread out over a small volume. And you think, okay, this one is +1, this one is +1, so did they behave the same? Would you expect these two to behave the same? Yeah, you'd expect them to behave the same because they're both +1. Since they're both +1, you'd expect them to behave the same. But then you'd expect them to behave differently because of what? How concentrated the charge is. And so the more concentrated the charge, the more force or the less force you'll have. The more force. And so the repulsions, if the positive charge is spread out over a large volume, like in the plum pudding model, then the repulsive forces aren't going to be as great as when the positive charge is concentrated in an extremely small volume in the center of the atom.
So in the Rutherford experiment, when they were trying to shoot the alpha particles through the foil, and they found out that they were getting through, does that have to do with the deflection?
Yes. So the question is, when the alpha particles go right through, it does have something to do with deflection. Here, these were undeflected. If they're undeflected, they aren't interacting much with either negative charge. Excuse me. If there are plums or raisins in here, let's say there's a plum here, or a raisin here. This is negative charge. If this is negative charge, then the alpha particle is going to see that and be deflected towards it. It wants to go towards the negative charge, which we'll write here. Does that make sense? So we expect small angles of deflection in the plum pudding model here. But what we see here is the same situation here. The electrons are out here, but it's mostly empty space. So, looking at the model here, we end up with this model. Since most of the alpha particles went straight through, most of the gold atoms consist of empty space. Some were deflected, either by the protons or maybe the electrons in here, and some were highly deflected, a small proportion. And so the plum pudding model was abandoned and replaced with the nuclear model of the atom. And so the nuclear model of the atom came from the observations of Rutherford gold scattering experiment. And that is, every atom contains a small and extremely dense nucleus. The nucleus contains all the protons and all the neutrons. In this statement, it says contains the atom's positive charge and nearly all of its mass. Nearly all of its mass must include the neutrons. If we look at the density of the nucleus, it's about 2 tons per cubic centimeter. What's the most dense element on the periodic table? Osmium or iridium, and those are how many tons per cubic centimeter? How many tons per cubic centimeter for osmium and iridium? What is the density of osmium and iridium roughly? Just take an estimate. 22 tons per cubic centimeter? Is that right? About 22 tons per cubic centimeter, meaning that those are even more dense than the nucleus. Is that right? Or did I mean to say 22 grams per cubic centimeter? Did I mean to say 22 grams per cubic? Yeah, I meant to say 22 grams per cubic centimeter. The density of osmium and iridium are around 22 grams per cubic centimeter. The density of the nucleus is 2 tons per cubic centimeter. Why such a huge difference? Could you even lift a ton? Can you imagine 2 tons, lifting 2 tons in the volume of 1 cubic centimeter? Is that possible to lift? It's so small, you should be able to lift it. But the reason why it's so high is because there's no empty space. You know, in atoms there's lots of empty space, and that empty space doesn't weigh anything. So the major volume of an atom is nearly empty space. That is, atoms consist mostly of empty space. The space outside the nucleus is thinly populated by electrons. So this is not truly empty. There are electrons there, but how big are electrons? Electrons are weird. They have 0 size. They do have mass, they do have charge, but they're weird. The space outside the nucleus is thinly populated by electrons. The total charge of electrons balances out the positive charge of the nucleus. So the number of protons in the neutral atom is equal to the number of electrons. This is for neutral atoms. The number of neutrons can vary, though. The number of protons is equal to the number of electrons for neutral atoms. The number of neutrons can vary. Ions will have an imbalance of protons and electrons. So this is the nuclear atom model that came from the observations from, what was the experiment that determined the nuclear atom model? The gold foil. And do you remember the guy's name? Rutherford. And so this is not a history class, but you need to know a couple of names. J.J. Thomson did what? Discovered the electrons using, what was that tube called? Cathode ray tube. And Rutherford used the gold foil experiment to do what? To describe the observations that were obtained from the gold foil experiment. Okay. All right, let's stop here for a break. Let's take a 15-minute break or so. So there are like certain questions in science. I mean, if you think about what scientists do, you know, scientists just try to do what? They try to describe nature. Okay? And so there are certain questions that come up that really don't kind of fit into science. So like certain things, like you could describe like the ocean is blue, the sky is blue, and what the process is there. But why blue? You know, why not green or some other color? And so we understand things at different levels. And so Coulomb's law says that opposite charges attract or repel? Attract, and like charges repel. But why is that? Why isn't it that like charges attract and opposite charges repel? Well, why that is unknown, you know, but when you look at matter, that's what it is, you know. And so there's certain types of why questions that aren't really easily answered in science, because science just describes nature. And that was going back to the scientific method. There are a lot of whys, and people will try to answer those, but when you go back just to fundamental science, then science is just a description, observation. So they were talking, I was watching, since I got this, since I saw some recent work on the UFO stuff, that got me interested in UFOs again. I was interested in UFOs when I was young, and so used to look at those all the time. But you know, they released, I guess the government released some new videos, and and the new videos, that's your observation, and then the description of what's happening. So people are describing some of those observations as artifacts. You know, those are just glitches in the electronics or whatnot, and that's what's causing the image to appear on the radar. And then there are other people who are trying to describe the observations as not glitches in electronics, but as an actual unidentified aerial object or phenomena. You know? And so those are just describing what's happening. So to answer a more fundamental question, like for example, why when an electron passes through space, why does an electron interact with, let's say, North Pole and the South Pole of a magnet? Why would it interact with a magnet? Well, in physics, what you learn is that when you have a moving charge, it generates a magnetic field. And then you might think, why does it generate a magnetic field? Well, in terms of science, that's what's observed. It's observed that it is generating a magnetic field. Now, why is it generating a magnetic field? That's a more complex question. You know, you could understand that, like maybe you could try to describe it more theoretically in it. And so I was looking at some posts on this. Where did I put it? On a stack. And so here, this is a question. How do moving charges produce magnetic fields? In physics, we just learned the laws. You know, if, for example, if the charge is moving at this particular current, what's the magnetic field strength that's observed? And that's something that you can measure experimentally. But when we come down to the reason why it generates, you know, then you can start getting deeper into theory. But then the ultimate question is, why does that even work? And so, like for example, in this stack, there are 7 answers to how do moving charges produce magnetic fields. And so the best answer that came up was a combination of electrostatics, which is Coulomb's law, with special relativity, which comes from Einstein. Einstein had general relativity and special relativity, and they're trying to come up with this. But it turns out this answer has some problems, apparently. And so there are people who are digging deeper into this type of stuff, and that's a good question, but for a lot of us, we just took it to the level where, well, that's what's observed, and that's what we have generated. It's like the, you know, it depends on how deep you want to go. Okay, there's some weird glitches that could be interpreted as alien spacecraft, or maybe not, but, you know, it's weird glitches or weird glitches. And how you interpret or how you explain those. Like one person, well, when I was at UCLA, there was one professor there. He was a professor of thermodynamics, Howard Reese. And he was a pretty renowned thermodynamicist, but he would always say this. He would always say that science doesn't explain anything, you know. Science just describes things. He always said that. So science never explains the why, it just describes the what. And I think to be safe, that's good, including the alien stuff. It's safe just to describe the phenomena. Well, let's get back to this here, and then so this is the structure of the atom. This is the atom. The atoms are approximately 10 to the minus 10 meters. 10 to the minus 10 meters, your book says that's falling out of favor, but 10 to the minus 10 meters is what we call an angstrom. An angstrom has the symbol capital A with a little circle on the top. That's the angstrom. And it's not a metric prefix. A metric prefix would just be the 10 to the minus 10. This is 10 to the minus 10 meters, so it includes the dimension meters. And that's the angstrom. So atoms are about 1 angstrom to about how many angstroms in diameter? An atom. An atom's between 1 and approximately how many?
600 microliters.
600 picometers, which is how many angstroms? A pico is 10 to the minus 12. So this would be, 1 angstrom is 100 picometers. And so it'd be between 1 and 6 angstroms. So I don't know which one's easier to remember, 1 and 6 angstroms or 100 to 600 picometers. But the question is, that's the size that's observed for atoms. Then a question might come up, why? Why that size? Why aren't they smaller? Or why aren't they bigger? Well, I don't know. You know, that's just the size they are. I don't know why they're that size, or specifically, you know, that type. And so that gets back to the why. But that's how big the atoms are. Now, how big are the nuclei? Nuclei is plural, nucleus is singular. How big are the nucleus? The nucleus is about 10,000 times smaller. And so if this were 1 angstrom, this would be 10 to the minus 4 angstroms. To put that in perspective, if the nucleus shown is 1 centimeter in diameter, then the diameter of the atom would be 100 meters. And so if you took like a football field, which is about 100 meters, and then right in the center you make a 1 centimeter divot, that would be the size of the atom in relation to, I mean, the size of the atom in relation to the size of the nucleus. So the nucleus is extremely small. This is why the density is so high. Because if the nucleus contains most of the mass, all the protons and neutrons are contained within the nucleus. The electrons don't weigh much. The electrons are just 2,000 times roughly lighter. And so all the mass is contained in this tiny volume. Most of the atom is empty space. And so when I ask you the density of osmium, iridium, that's 22 grams per cubic centimeter, but the density of the nucleus is about what? About 2,000, about 2,000 pounds per ton. We got 2 tons. It's about 4,000 pounds per cubic centimeter. Enormous. And so the density of the nucleus. But when the alpha particles come, the reason they bounce off is not because of the mass. You know, this is very massive, partly due to the mass. The reason they bounce off is because of the Coulombic force. The alpha particle's positive, the protons are positive, they're going to repel each other. And so that's why they bounce off the nucleus. Okay, and then we have this empty space region that's occupied by electrons. So this is the basic structure of the atom.
I have a question. I think it was in my test book. It was like about Coulomb's law explaining the attraction of particles. But I thought Coulomb's law was about the total charge.
Coulomb's law is, the question is about Coulomb's law. Coulomb's law just is describing the force of attraction or the force of repulsion between particle A and particle B, divided by the distance between the centers of the particles squared. And so Coulomb's law is just saying this. We're looking at the force of attraction. So we have a positive and negative here. Those are going to be attracted to each other. But what if I did this? What if I made the positive plus 2 and the negative is still the same?
There's then the overall charge of 2 particles is positive.
And let's say the sizes were about the same. And so what would the force be here? Well, the force would be plus 1 here for the charge, minus 1 for the charge here, and then we have the distance. Here the force is plus 2 for A, and B is minus 1, the same. The distance is about the same, and therefore we'd say the force is 2 times stronger in this than this. And so the force is going to be about 2 times stronger. And so we'll call this we'll call this 1, and we'll call this the force 2. It'll be about double the force of 1. Does that make sense? So Coulomb's law is just talking about the interaction between particles, between charged species, not the total charge. The total charge, what's the total charge on 1?
So it would be neutral?
Yeah, this would be 0. What's the total charge here?
+1.
It's +1, but it doesn't matter what the total charge is. We're looking at just the interaction between these 2 particles, A and B. That's
So
it.
it is about like attractive and like negative and positive charges
Right.
being attracted to each other.
Right, how they're attracted to each other. Now, the distance is also going to play a role in there. So if we concentrate the charge, so let's keep the charge at +1. Which is going to be stronger? This is scenario 3. Here. Force 1 or force 3? So the difference is in how concentrated the positive charge is. Here you have a positive charge spread out over this sphere. Here you have a positive charge, but it's spread out over a much smaller sphere. So which one has a more concentrated positive charge? The bottom one, number 3. So when it comes to 1 versus 3, 3 is going to have a stronger force. Do you see that? Because the charge is more concentrated. And so this is how you have to use Coulomb's law. This is the way we use it.
But Coulomb's law doesn't seem to really care about the density of that charge. Since it's just a charge overall.
The density is not directly in here, but the density is dependent on the distance. The further apart these are, then the less dense it is. The closer they are together, then the more dense it
Yeah,
is.
but I remember force 1 and force 3 are the same distance, but force 3 is still stronger.
No, they aren't the same distance, because the way we measure distance is different. When you measure the distance here, there's 0 distance between them. They're touching.
Yeah.
And the same thing here. When you measure the distance, they're touching. But this distance is a little bit different. This distance is between what we call the center of charge. And so the actual distance looks like this. When I measure the distance, I don't measure it here, which is 0. I measure it from the center here to the center here. And this is the distance. It's called the distance between the center of charges. When I look at the same thing here, I go to the center here and the center here and then measure the distance. Which one has a shorter distance?
Force
3 has the shorter distance. And so therefore it's going to have a stronger Coulombic attraction. And therefore it's related to the density, because all these things are touching. And so the distance between is 0, but the distance between the centers is not. So this is just a summary of what was the experiment for the nuclear model? Yeah, it's the Rutherford Gold, which is AU foil experiment. In the Rutherford Gold foil experiment, most alpha particles were not deflected. And what that implies is that atoms are mostly empty space. The fraction of particles slightly deflected as they pass through close to the nucleus are pretty small. The particles near the nucleus are repelled by positive electrostatic forces, these Coulombic repulsions, we call it. A small number of particles on the collision course with the nuclei were repelled backwards, and those went straight into the nucleus. There's going to be strong electrostatic repulsions there. Okay, we looked at these subatomic particles already. All right, so now we know the composition. So there's a way of representing the composition. And it turns out that hydrogen, the element hydrogen, has 3 different compositions. And so what are the 3 different compositions of hydrogen? The 3 common compositions of hydrogen. And we call these different compositions of hydrogen isotopes. Isotopes are the same element, hydrogen, for example, but with differing numbers of neutrons. The different numbers of neutrons will give it a different mass. All isotopes, or all atoms of hydrogen, have 1 proton here. But the number of neutrons vary, so the number of protons stays fixed at 1. So the first isotope has 0 neutrons and 1 electron. The next isotope has 1 proton, 1 neutron, 1 electron. And the third isotope has 1 proton, 2 neutrons, and 1 electron. And so these are the 3 common isotopes. Common, I have to put a little asterisk there because number 2 isn't that common, and number 3 is kind of rare, extremely rare in natural waters. But these are, there could potentially be more, but those we wouldn't even consider as very common. Those would be very short-lived. So we'll talk about the total contribution of the mass, but isotopes are 2 or more atoms of the same element that have different masses. The reason they have different masses is because they have a different number of neutrons. And so what we're going to do is we're going to identify certain things compositionally. The first thing we're going to do is we're going to come up with something called the mass number, A. The mass number is equal to the total number of protons and neutrons in the nucleus of an atom. So A, the mass number here, is equal to Z. Z is what we call the proton number, the element number, or the number of protons, or the atomic number. And N is the number of neutrons. So the number of neutrons we don't give a special number to, but the number of protons we do, and that's Z, or the element number. Since all hydrogens have the same number of protons, therefore, if we have an atom with 1 proton, it's got to be hydrogen. All atoms of helium have 2 protons, but the number of neutrons might vary. And so the weird thing about the mass number is the mass number is not equal to the mass. That's what I'm writing here. The mass number is equal to the number of protons plus the number of neutrons, which is just a number. However, it's close to the mass because the protons weigh about 1 U, the neutrons weigh about 1 U. The electrons don't weigh much. So if we ignore the electrons, then the mass number and the mass are close to one another. So this is what I say, it's about equal to the mass of the isotope. The isotope being the atom of an element, but with different number of neutrons, different mass. Okay, let me go on to the next one. So let's take a look at naming isotopes and then determining their composition. So if we name those 3 hydrogen isotopes, the first one we call hydrogen 1, the second hydrogen 2, and the third one is hydrogen 3. And the name comes from this. The 1, 2, and 3, this is the mass number. And so we have hydrogen with a mass number of 1, hydrogen with a mass number of 2, and hydrogen with a mass number of 3. All these will have the same Z or the same atomic number or the same element number. So Z is equal to 1, which is equal to the atomic number, which is equal to the element number. And so hydrogen's element number 1. And we recognize that because it has 1 proton in this case. 1 proton for hydrogen. And so we don't have to write a Z here. Some of these hydrogens have a special name to them. So for example, hydrogen 1 is often just called hydrogen, but hydrogen 2 gets a special name, deuterium. And then hydrogen 3 gets a special name, tritium. Tritium, however, is unstable. tritium, it turns out that the number of neutrons plays an important role in stability. It's thought that the neutrons are what holds the nucleus together. So if we go back to this, there's something weird about this figure here. If we look at this figure, we talked about if a alpha particle comes in. Alpha particle has what charge? Positive. And if it gets close to the nucleus has positive charge, we get electrostatic repulsion. But neutrons are neutral. They have no charge. But protons, these red ones here, are positively charged. And so if you look at these two protons, they're touching. And didn't we just do this over here? Unlike charges attract. So there's a force of attraction between the positive and negative here, but like charges do what? Repel. And so here I have two protons, and each proton is +1. Why are they stuck together? In fact, this thing has a density of 2 tons per cubic centimeter. That means they're really crammed in there. How can you cram 2 protons in there like this? Aren't they going to repel each other? Wouldn't this whole thing just fall apart? And so the answer to this is there's something holding them together, but whatever's holding them together has to be stronger than electrical forces. Do you know some force that's stronger than electrical forces? Gravitational is weaker. There is a force that's stronger. Do you know what it's called? It's called the nuclear force. There's a nuclear force that can overcome electrical forces that holds it together. And so we divide this chemistry into regular chemistry, which deals only with electrical forces, and nuclear chemistry. Nuclear chemists could care less about electrical forces because electrical forces are so weak they're insignificant. For chemists, electrical forces are the most significant. But for nuclear chemists, electrical forces are too weak to even consider. Because what holds the nucleus together are, well, there are 2 electrical forces that people commonly think of. There's the weak electrical force and the strong nuclear, excuse me, not electrical. Let me back up. There are 2 nuclear forces that people think of. The weak nuclear force and the strong nuclear force. So what must be holding these protons together? The weak nuclear force or the strong nuclear force?
Strong.
You would think the strong are holding it together, but you know it's not the strong. You know what's holding it together? The weak nuclear force. So the weak nuclear force can overcome Coulomb's law because the forces are much stronger and hold the nucleus together. Otherwise this whole thing would fall apart. You got so many protons. In fact, all the positive charge is concentrated in this nucleus. How can that be? And so the weak nuclear forces are holding it together. Well, what one hypothesis is that the neutrons are the glue that holds the nucleus together. That's one. And so we need the right amount of glue. Too little glue means the nucleus is unstable, and too much glue does the same thing. Too much glue means the nucleus is unstable. So in tritium has too many neutrons. Tritium's radioactive. It's got 2 neutrons, well, that's too many. Deuterium's okay. Do you know, if this is weak, then what's strong? The strong comes from what holds the proton together. The proton's made up of even smaller particles called quarks. And so what holds the quarks together are the nuclear strong forces. And so in order to break protons apart, it's going to take even more energy than to break the nucleus apart. And then there are, so this is the realm. We don't deal with what we call nuclear chemistry. nuclear chemists are looking at, you know, chunks of atoms, chunks of the nucleus breaking off. So if I have 2 protons and 2 neutrons break off, that's called an alpha particle. There are no electrons. So we got 2 protons, 2 neutrons, that creates the positive alpha particle. And so if we have a nucleus that's too big, you know, it's got too many protons in there, chunks of it might break off, and we call that radiation or radioactivity. So going back to this, you know, tritium's too many neutrons there. It's going to be radioactive. So really hydrogen and deuterium are the 2 that we are concerned with. And the way we name them, so for example, this hydrogen 1, then we can represent the composition using the nuclear symbol. And the nuclear symbol, what we do is we have the symbol H, and then down on the lower left we write the number of protons, which is also called the atomic number, which is also called Z. So on the bottom left we write Z. Well, Z is the number of protons, or the element number, which is 1. And so the Z for hydrogen is always 1. However, up here in the upper left we write the number of protons plus the number of neutrons, which is also called the mass number, which is also called A. And that's, in this case, for the first one, we have 1 proton, 1 electron, and 0 neutrons. So that's mass number of 1, so that's hydrogen 1. And then this would be hydrogen 2, the mass number of 2, and this is hydrogen 3. And so we can figure it out based on that. So let's take a look at the nuclear symbol for carbon-12 and carbon-13. And so what element is carbon? The Z is written in red on the periodic table up here, and if we look at carbon, carbon is element number 6. And so that goes down here on the lower left. And 6 means we have 6 protons here. Now carbon always has 6 protons. And so carbon-12 is one, what we call isotope. Carbon-13 is another, but it has 6 protons. Carbon-14 is another, but carbon-14, is that stable? Now carbon-14 is radioactive, and carbon-14 is used for radiocarbon dating. It's got too many neutrons. We'll talk about it later. But this is 6 protons here as well. So they all have 6 protons. The 6 protons means it has properties of carbon. Now the number of neutrons can vary. So in carbon-12, we're going to have 6 protons. And then how many electrons? Well, if there's 0 charge here, the electrons are balanced. So if we balance out the positive charge with the negative charge, we get a neutral atom. This is not an ion. This is just a neutral atom. And so the number of protons equals the number of electrons for neutral. If this were an ion, then the number of protons and the number of electrons are imbalanced. Now the number of neutrons we figure out based on this. The number of neutrons is not 12, but we know 6 plus the number of neutrons equals 12. So the number of neutrons must be 6. So 6 plus 6 gives us 12. And then we go on to carbon-13. How many neutrons do we have here? 6 plus the number of neutrons is 13. So the number of neutrons is 7. So 6 plus 7 is 13. All these have 6 electrons because all these are neutral. And then we go to carbon-14. How many neutrons does carbon-14 have? 8. And that gives us our composition. Okay, this table I need to... I should have just started. Let me delete this. Let's do this table next. I'm going to do this in a Word. Actually, that's the key. Oh, this didn't quite work out. Well, we'll just go through it. Tried to erase this all at once, but I'll just erase it here. All right, so we're just going to try to figure out the composition of these. And then so what's the symbol for barium? The symbol for oxygen? Oh. Normally when we think of oxygen, we think O2. But now we're just looking at the composition of the atom, so in this case we'll just think of O. The symbol for the next one, what is the next one here? I must have erased it by accident. Let me do something here. Let's just start off with a clean sheet. So we have barium and then oxygen. And then what is element number 82? Lead. What's the symbol for lead? PB. So we'll do that here. And then this, what element is this? Zinc. And the symbol for zinc? Zn. Okay. What element number is barium? 56. Oxygen? Zinc? Okay. And then how many protons do we have for barium? 56. So the number of protons defines what element we're dealing with. So anything with 56 protons is barium. Oxygen? 8. 82. 30. So these ones we're going to have to figure out. The number of neutrons varies. So we need additional information here. And the additional information is going to come from this. So remember, 56 protons plus X neutrons gives us 138. So, what is it?
82.
82. So that means 56 plus 82 must equal 138. Is that correct? Yeah. Okay. Then we're all right. Over here, we have the number of protons, it's 8, and we have the number of neutrons. So the mass number will be 18. Now the mass number is close to the mass, but not exactly equal to the mass. So this weighs about 18.
Not for barium.
Barium's what?
Because barium, it's like 9.
Barium is
The mass is 9.
130. Well, we'll figure it out. Barium, this barium is going to weigh about 138.
Oh, wait, not barium. Wait, what's Be?
Beryllium. Beryllium. How about this lead? How many neutrons do we have here? So 82 plus blank gives 206. Would it be 124? Is that right?
Yep.
Yeah. 82 and 124 gives us 206. 30 plus blank gives us what? And so the mass number, oh, here is the mass number. The mass number is 66. So 30 plus what gives us 66? 36. So that's the number of neutrons. Mass number is the number of protons plus neutrons. Those are okay. Now let's do the nuclear symbol. In the nuclear symbol, we write Z on the lower left. And so this would be oxygen, and the Z is 8. And then A on the upper left, which would be 18. And we call this what? Oxygen 18. Oops, oxygen hyphen 18. Should I fix that? The one above it's called what? Barium 138. What is this one? The symbol for this? PB 124 up here and 82 down here. And this would be lead 124. And finally, zinc 66 and 30. Okay, this would be. Oh yeah, the lead is 206. That's correct. Thanks. Let me fix that here. It's the atomic number, not the number of neutrons that we have. We can figure out the number of neutrons just by subtracting these two numbers. It'll give us the number of neutrons. So this tells us the composition. So what we want to do is we want to be able to correlate the composition, the structure, with the properties. So could you do it? Could you tell me the properties? Okay, let me say I have element number 19. If I have element number 19, what are the properties?
Is it an alkali metal?
It's an alkali metal, yeah. The way you do that is you look at the periodic table, because the periodic table organizes things based on properties and composition. And so let's take a look at how we're going to do this. Right now we can't do this easily. So let me go through here. Actually, I'll jump ahead a little bit. But certain things come up. So, for example, if we were to add one proton to hydrogen, then we have two protons, which would be helium. And so we might say, okay, by adding one proton here, that's the properties went from hydrogen to helium. Helium's non-flammable. Helium's relatively what we call inert. Hydrogen is very reactive. But then if I take helium, which has two protons, and add one proton, we go to lithium. Well, lithium's more hydrogen-like. But then if we take lithium and add one proton, we don't go to neon. We go to beryllium. Beryllium's highly toxic. And so, do you see a pattern there? Could you predict? So let's say I went from 33 protons to 34 protons. Can you tell me how the behavior is going to change? Well, we can kind of figure out, 33, where's 33? It's over here. When we go from 33 protons, arsenic, to 34, it goes to selenium. Could you have predicted that? And what could you have predicted with the properties? Well, all we could do is we could just look at the periodic table and try to make a correlation that way, but we don't really understand this quite enough. I mean, there are some patterns here. You see, one of the patterns here is, let's go with this group, the alkali metals, we call them. The alkali metals because this group has similar properties. So when we go alkali metals, it goes from 1 proton to 3 protons. So that's plus 2. And then if we go 3 protons, what's the next one? 11 protons. That's plus 3 plus what gives us 11? 8. And then we go from 11 protons to potassium, which is 19. That's plus 8. So maybe the next one we predict should be plus 8. But what is it? Well, we're going from 19 to 37 protons. Is that plus? No, that's not plus 8. Do you know what that is? It's plus 18. And then we go from 37 to 55. How many is that? That's also plus 18. So there is some kind of pattern there. It's 2, 8, 8, 18, 18. 18. So there is some sort of pattern there, but how can we use it? And so what we say is this is just the beginning. We don't have enough composition and structure to really understand the properties just quite yet. You know, our understanding of the composition and structure of matter isn't adequate enough to make somewhat accurate predictions on properties. And so we need more information. So we're going to leave it at that for right now, and we're going to look at some other stuff. And the other stuff we're going to look at is something called the atomic mass. And the atomic mass, this is called the average mass. And so let me say, let's do some averages here. If I have, let's say, one thing that weighs 50 pounds and another that weighs 100 pounds, what's the average? 75 pounds. That would be the average. But what we're going to do is we're going to do what's called a weighted average. And so we should call this the weighted average mass. And the difference is, in a weighted average mass, it depends on how many of these you have. Let's say you look at a group, and this group consists of (1,000) people. And out of this 1,000 people, let's say 999 people weigh about 100 pounds. And then one person weighs 50 pounds. And then what is the average? Is the average still going to be 75 pounds? No, what would the average be? The average person in this group would weigh about what? Could you figure it out?
Yes.
Yeah, we could figure it out using some algebra. And the way we do that is something like this. We'd say 999 out of 1,000 weigh 100 pounds. And then we just add that 1 out of 100 weighs 50 pounds. And then we could get what's called the weighted average. The weighted average is going to have the fractional percentage or the decimal. So we could use fractional or decimal. We call this the abundance, or the number, times the mass. And so this fraction has this mass, and this fraction has that mass. And what is the weighted average? Well, we just calculate it, and that would give us the weighted average. Well, the same thing for atoms. And let's take a look at doing this for atoms. So I have hydrogen here, and I have deuterium here. Tritium's not on here because tritium's radioactive. And then I look at a sample in nature. This is the percent, what we call natural abundance. And so if I get a sample of hydrogen, then 99.9885 of those out of 100 will be hydrogen 1, and then 0.0115 will be hydrogen 2 or deuterium. And so probably the easiest way to visualize this is like this. I'm going to move this over 1, 2, 3, 4, and move this over 1, 2, 3, 4. And so what this says to me is, in terms of fractional abundance, 999,885 out of 1,000,000 are hydrogen 1 and weigh this much. And then this one would be 115 out of 1,000,000 weigh this much. It's twice as heavy. And so in other words, if I had 1,000,000 hydrogens, only 115 of those would be hydrogen 2. And so if I were to average it, what would the average mass be closer to? Would the average mass be closer to 1, or would the average mass be closer to 2? It would be much closer to 1. In fact, the average, or the weighted average mass, is what's given on the periodic table. And so when I take a look at the periodic table here, I see some numbers. This number on the top is what? Atomic number, which is the number of protons, which is called Z. This number on the bottom, do you know what that is? That's the weighted average mass of the hydrogen. So there are two weights for hydrogen atoms. One weighs 1, the other weighs 2. The average is close to 1, which means hydrogen 1 is much more abundant. We could go ahead and calculate it. So let's go ahead and calculate it. This number's been rounded, and so let's try to get a more precise number using the data that we have. And so I'm going to take the data here off the table and use this. To calculate the average down here. Oh, that's not it. Get it. All right, so if I want the average, I'm going to take the fractional abundance, which is, I'm just going to leave it as 99.9885 out of 100 will weigh 1.0078250,321, plus the other fractional abundance, which will be 0.0115 out of 100. These are percent. Actual abundance will weigh 2.014117780. All right, since I'm mixing up sig fig rules, what I'm going to do is I'm going to do the multiplication here first, multiplication and division on both ends there. And so I could convert this into decimal form if I want, but I'll just leave it in fractional. So 99.9885 times 1.00 782 50321. Divided by 100. All right, how many sig figs am I allowed in this first calculation here? I'm allowed 6 is correct. I have 6 figs in the numerator, infinite sig figs in the denominator, and more than 6 here in this number. So I'm going to have at least 6 sig figs. So I'm going to go 0.00782. How many sig figs is that? 3. And so I'll go 413. And then what I'm going to do is that 6 sig figs, I'm going to carry one extra digit to minimize rounding error. Okay. And so the units here are U, atomic mass units. So this is U. So this is the first number here. Now the second calculation is also going to be multiplication and division, and I'm going to write this down here. So this one is going to be 0.0115 times 2.014 778 778U, sorry. And that's going to be divided by 100. How many sig figs am I allowed in this? 3. So this is going to be point 0, these zeros, point 0.000 231. And then I'm going to carry one extra digit to minimize rounding error. So this is 3. How many sig figs am I allowed in my final answer?
Are you adding them?
Hmm?
Are you adding them?
No, I'm adding them. Let's see, I'm adding them here. So if I add, how many sig figs am I allowed? We don't do sig figs when you do addition. We do what? Decimal places. So which one has fewer decimal places? This bottom one. How many decimal places do we have? 1, 2, 3, 4, 5, 6. We have 6 decimal places. So this is the uncertain digit, and this one's not allowed. We're only allowed 1 uncertain digit. I have 2 to minimize rounding error. And so up above here, I need to, or actually down here, I need, this digit's going to be uncertain. So I'm only allowed 6 decimal places. So I'm going to take this number plus 0.00782. I'm going to just use all the digits. 4132. And that's going to give me this as my final answer. My final answer is going to be 0.00. That's 2 decimal places. 8, 3 decimal places. 05. Oops, I made a mistake there. 05. That's 1, 2, 3, 4, 5, and then 5. 6. I made a mistake here in my calculation. Sorry, let me correct it. This should be 1.00782.413. Can somebody verify that? And so this needs to come out to 1.008. And so this is what we have. So we could be a lot more precise here, but there's not enough room. Since there's not enough room, we'll just go 3 decimal places. What we do here for these is most of these are going to be to 2 decimal places. And so we'll just round it to 2 decimal places. We could have more. To save space. To save space, and there are other reasons for it too, etc. Hydrogen often will go 3, but most of the others will just do 2. All right, when we look at this, it doesn't tell us how many isotopes there are. So when you look at this number, it's just the average. It's the average of all the isotopes. How do we know how many isotopes there are? And how do we know what the masses of those isotopes are? How we know that information is by measuring it. We have an instrument that measures this. The instrument that measures this is called the mass spectrometer. And so, let me talk about the mass spectrometer here. The mass spectrometer measures the number of isotopes and their mass. But we also get one more thing. And that one more thing is the what we call the percent natural abundance. Or the relative abundance here. And so what we see, this is called the mass spectrum of neon. When we look at the mass spectrum of neon, we see that there are 3 isotopes. One with a mass close to 20, so this would be neon 20, because if the mass is close to 20, then the protons and neutrons must add up to 20. And so we'll just say that the mass is close. But we could get the mass to many sig figs, like 9 sig figs here. It's not shown because there's not much room. We have another one at 21 and another one at 22. And the way this works is the height of this peak depends on how many atoms strike the detector here. So the most abundant one will be 20. And if we normalize the 3 to add up to 100%, then we'll get the percent natural abundances. So if these 3 add up to 100, then this is going to be something like 80% or whatever, and this is going to be another percent, that's going to be another percent. Now, when we look at the mass spectrometer, we can see how it operates here. The mass spectrometer operates similar to a cathode ray tube, except rather than having a beam of electrons, you have a beam of ions. And so the first step in mass spectrometry, there are 5 stages here. The first step is to vaporize. So we need to vaporize the sample. There's different ways we vaporize it, actually. Let me stop here. One way is to heat it up. Other ways is it's already a gas. If it's already a gas, neon's a gas, so you don't have to vaporize neon. But if it were liquid or if it were a solid, we'd have to vaporize it. We could vaporize it by heating it up or using a laser to vaporize atoms on the surface. The next step in this is to get a charge on there, and that's ionization. So we use a cathode ray. What is a cathode ray? A beam of electrons. So we could use cathode ray here to shoot electrons to create ions. Or we could shoot other things. We could shoot small atoms or particles or molecules at that. In other words, we're going to get a charge on there. If there's a charge on there, then we can accelerate that by putting, let's say, if there are negatively charged particles, we put like a cathode here. Cathode's positively charged. So the negative and positive attract, and then these will be accelerated towards the positive. If these are positively charged particles, then we put the anode, which is a negative electrode, a negative piece of metal here, and that will be accelerated there. And so we'll accelerate these by using what's called an electric field.
Accelerated force.
And then
it is deflected.
the deflection. The deflection is going to come when you place a magnet here. If you put a magnet here, it depends. The more massive ones are going to be slightly deflected, whereas the lighter ones will be heavily deflected. And so you can separate the atoms based on their mass.
And
then they'll strike the detector down here. So that's the section, the final step here. And so let's take a look. Okay, here's the deflection with the magnet. They didn't show the magnet earlier, but we can see it has to be charged. If it's not charged, it'll just go straight. But the heavier ones will be slightly deflected. The light ones will be more heavily deflected. And this is what they did with electrons. With electrons, from the physics of the deflection here, the angle of the deflection, they could get something called the charge to mass ratio. And from the charge to mass ratio, then Millikan figured out what the charge is. You don't have to know about Millikan, and then they were able to calculate the mass using dimensional analysis. But we get the charge to mass ratio. But how do we calibrate it? How do we calibrate this? We need something that weighs exactly 1 AMU. Is there something that weighs exactly 1 AMU? No, but there is something that weighs exactly 12 AMU. And did I talk about that already? No, I didn't talk about that. And so let me talk about that right now. Make sure. And that is, what is the definition of the AMU? There isn't anything that weighs exactly 1 AMU, but there is something that weighs exactly 12 AMU. And that thing that weighs exactly 12 AMU is carbon 12. And so let's do that here. So 1 AMU is 1/12 the mass of a carbon 12. Can you divide a carbon 12 atom into 12 equal pieces? No, it's impossible. It would just break up into subatomic particles, so that's not possible. But this is the definition of 1 AMU. 1 AMU is 1/12 the mass of 1 carbon 12 atom. I don't use this definition. Instead, I use this definition, 12U. 12U is defined as the mass of a single carbon 12 atom. And so what weighs exactly 1U? Nothing weighs exactly 1U. What weighs exactly 12U? Well, carbon 12 does. And so what we do is we feed carbon 12 into the mass spectrometer. Where carbon 12 hits, we set the detector to read exactly 12U. Now, carbon 12 is what we call the new definition. There is an old definition of the U. The old definition is like pre-1950s. If you look at the old periodic tables, in the old periodic tables they have different average atomic masses. The reason they have different average atomic masses is because in the pre-1950s they defined the AMU based on oxygen 16. What they said is that 1 oxygen 16 atom weighs exactly 16U. Well, if 1 oxygen 16 weighs exactly 16U, then that tweaks carbon. Carbon's going to be offset a little bit, and so carbon 12 is no longer going to weigh exactly 12U. So all the masses in the old periodic tables are off a little bit. And then if we go to carbon 13 does not weigh exactly 13. Carbon 13 weighs close to 13. It's off a little bit because of how the masses add. So the only thing that weighs exact is carbon 12. And so if we introduce carbon 12 into our mass spectrometer, then we can use that to calibrate it to make sure it's reading correctly. Here. And so we calibrate the mass spectrometer with carbon-12. Well, once we've done that, then we can figure out the precise and accurate masses for a lot of other isotopes. So we don't always have to use carbon-12. We could use other isotopes and figure out where those hit. We'll just plug in the mass. So the mass spectrometer works similar to what a cathode ray tube does. And so let's take a look at an example here of analyzing a sample of particular element. And so when they introduce this element here, this is the mass spectrum. So this is what they're seeing at the detector here. And depending on how many strikes, each time it strikes, then one of the peaks will grow. That peak will grow here. And so what they can do here is they see that there are 2 strikes. That means there are 2 isotopes. And based on the relative heights, we can get the percent abundance. And so we get the number, 2, the abundance, the height, and the masses. The masses, once we calibrate this, this will measure to 9 sig figs. They aren't showing the masses to 9 sig figs, but we can easily get it to 9 sig figs here. So here they're introducing rubidium. Let me speed this up.
For an example, here's some mass spectrometer data from a natural.
So how many isotopes are there for rubidium? 2. And their abundances are shown here. Rubidium 85 is about 77%. Rubidium 87 is about 23% abundance. Now, it depends on where you collect the rubidium. There could be small variations. So, for example, if you collect oxygen, you can take a look at oxygen here. It depends on the source of the oxygen. And so, if we go back here, we're going to collect all this data and plug it into a table like this. And so we saw hydrogen here already, and then we saw oxygen. The heaviest oxygen that naturally occurs is oxygen 18. We also have oxygen 19, but that's radioactive. But oxygen 18 is stable, but it's not very abundant. It's got a mass of 17.9991604. So that's, how many sig figs is that? That's 9 sig figs. We can get that mass too. Now, what are the other isotopes of oxygen? The other isotopes of oxygen that we have are oxygen 16 and oxygen 17. And so what happens is this. There's some light oxygen, and then there's some heavier oxygen. And so if you look at ozone, in the ozone layer, the composition of the ozone in the ozone layer is richer in oxygen 16 versus the composition of ozone on the surface of the Earth is richer in oxygen 18. And so there's slight variations in the percent natural abundances depending on where you get the sample. So if you go to the bottom of the ocean is going to be richer in heavy water. Have you heard of heavy water? Heavy water has, like, say, deuterium instead of hydrogen there. Versus at the surface. So the heavier molecules and the heavier atoms sink to the bottom. This is due to gravity. We call that fractionation, isotopic fractionation. And so you would expect, like, there to be some small variations in and so this is an interesting paper here. This was in 1993. But they're looking at isotopic fractionation of oxygen by respiring marine organisms. So could they figure out what depth the marine organism lived at depending on the percent natural abundance of the oxygen that they have? And so they looked at enrichment in oxygen 18, relative to atmospheric oxygen. And so the deeper you go, the more 18 you would expect because that's heavier. and the heavier ones would sink lower. And so they tried this. They tried to support a hypothesis, you know. But what happened is they had a high variability that limited the usefulness of this. But still, geologists use this, and other scientists use this. It's easy to tell the difference from ozone in the ozone layer versus ozone from pollution on the surface of the Earth. It's easy to tell based on the fraction of the isotopes that are found in it, the samples. So this is all from mass spectroscopy and mass spectral data. A couple of things here that you might notice. It's hard to predict how many isotopes. For example, sulfur has 4. Beryllium has how many? Only 1. And that 1 is 100% natural abundance. So all beryllium atoms weigh this. But all carbon atoms don't weigh this. The average carbon weighs 12.01. This is like 99% carbon 12, 1% carbon 13. And so 12.01 is the average of those. Over here, fluorine, only 1. It's 100% abundant. So all of them weigh this much. But what about chlorine? What do you think the average of chlorine is? Can you just look at it and see? If we look here, we can figure it out based on this here. If it were a 50-50 mix of chlorine 35 and chlorine 37, then the average would be 36. But when I look at the periodic table, what is the average on the periodic table? The average on the periodic table is 35.5, which means there's more 35 or more 37? There's more 35. So if this is 50%, then this must be, this is halfway between, this must be 75% chlorine 35. And so that's what we see here. The average is 35.5, therefore it's about 75% chlorine 35, 25% chlorine 37. So we could eyeball it or we could calculate it either way. And so over here, we can just eyeball, what's the average mass of oxygen, you say? 16. This is 99.8% oxygen, 16, so the average is going to be very close to 16. What is it? It's about 16.00, rounded to 2 decimal places. Okay, let me just finish off this chapter here. Okay, so that's the mass spectral data. And then we have everything organized in the periodic table. I just have to name certain things. What are these columns called? Groups or families. And so we have the alkali metal family, or group 1. Group 2 is called the alkaline earth, etc. And so we have groups. And then the rows are called periods. And what happens with the properties in a period is they gradually change. And so each step in a period, we're gradually changing from what we call metallic properties to non-metallic properties over here. And then what else do we need to know for the periodic table? Periods, we need to know main group, transition elements, metals, nonmetals, and metalloids. Let's go back here. Do you know what the main group elements are? The main group elements are these first 2 families and these last 6 families here. And so the main group is this first block and the second block. This block in the middle is called the transition element, so we're transitioning across. These are the lanthanides and the actinides. And then all the elements on the left are metals except for hydrogen. Hydrogen does have some metallic properties. And then all these elements on the right are nonmetals. And then we go through this transition zone where we switch from metal properties to non-metal properties. In this transition zone we call the metalloids. The metalloids are kind of a cross between a metal and a non-metal. And so metalloids would be like silicon, kind of cross between a metal and a non-metal. Aluminum's more metal. Germanium, arsenic, those are metalloids. Antimony, tellurium, metalloids. These are metalloids here. And then that's pretty much it for chapter 5. So take a look at chapter 5 and the homework there. And if you have any questions, we'll go through those. But otherwise, we're going to start chapter 6 tomorrow, which is nomenclature. Okay, I'll end here.